Hello everyone, welcome back our class. Let's continuously study the chapter 4, convertibility of energy, exergy, analysis. In this section, we will study several examples of exergy analysis, especially to calculate the exergy. Here is a very typical example. A heat transfer process in a plate is shown as the figure. Here, the environment temperature is TA. The conductivity of the plate is K. Calculate the exergy change between two surfaces of the plate. How much entropy generation will be produced in the process? Just tell us, here is a plate. Because the left side of the surface, the temperature is T1 is larger. Left side, the temperature T2 is lower. The thickness of the plate is X. In this case, certainly there is some thermal energy transfer from T1 to T2. In this process, certainly is not reversible process. There is some work loss, exergy destruction. Solution. The heat transfer in the plate will be very easy to calculate. Is Q equals K T1 minus T2 over X. From the heat transfer theory, it's very easy to obtain this equation. Just the conduction equation. Under environment temperature TA, the heat energy before passing through the plate is, we can calculate respectively. In the surface 1 is EXQ1 equals K. K is the conductivity. T1 minus T2 over X is the Q, small q, times Carnot ratio is 1 minus TA over T1. The heat exergy after passing the plate, there is some change. So EXQ2 equals K times T1 minus T2 over X, here is the small q, times 1 minus TA over T2 is the Carnot ratio. So the exergy destruction in the temperature difference heat transfer, we can calculate EXQ1 minus EXQ2 equals K T1 minus T2 over X times 1 minus TA over T1 minus 1 minus TA over T2 is two terms minus. We easily to calculate, obtain K times T1 minus T2 over X times 1 over T2 minus 1 over T1 times TA. TA moves out from the terms, from these two terms, minus out. So we obtained the exergy change, exergy destruction. In this case, exergy destruction means the entropy generation produced. So DSG equals EXQ1 minus EXQ2 over TA. Finally we can obtain the entropy generation. This example is not so difficult, but a little difficult to think about it. How to calculate the method, how to think about it is a little difficult. Okay, another example, just how to calculate the entropy generation ratio. We use the conduction and convection to calculate it, to discuss it. The left picture is a bar outside is insulation. So no heat energy losses. The heat energy just from T1 transfer to T2. So another picture is a plate convection to the must stream, to the must host stream. So this picture means a convection problem. Another picture is conduction problem. Here we only discuss the conduction problem. Convection problem is similar, be easy to understand. Okay, for conduction problem, we can do some analysis by element. For example, in the bar, we can take an element to analysis. Before the element is Qx, after the element is Qx plus dQx. The temperature is Tx become dx. So in this case, we can calculate the entropy change in an irreversible process. The heat transfer certainly is irreversible process. Entropy generation will be produced, DSG. For unit time, energy generation ratio is gamma is DSG over dt, means unit time to produce the generation, entropy generation. So for unit time and unit volume, the entropy source strength is sigma equals DSG d over dt, unit time, unit volume. So means strength, means entropy source strength, In steady state, in any place, the heat flux is Q, because from T1 to T2, the heat transfer is constant. So Q is constant. So the entropy change, the total entropy change is Q over T1 minus Q over T2 is the entropy change, total change. So the heat flux is easy to calculate. Unit area, the heat transfer. So JQ means the heat flux is Q over A is the section area, equals minus lambda dt over dx. dt over dx is the temperature gradient. So minus means because the heat transfer always from the direction is from high temperature to low temperature. So dt over dx always is minus. So we add a minus together is positive. So equals lambda T1 minus T2 over TL. TL is the total length. At any section, the entropy flux is Js. The heat flux is Jq. Here, the entropy flux is Js. Js is Jq over T equals minus lambda over T dt over dx. Here is the, in any section, the entropy flux. The entropy generation ratio in dx is gamma is dsg over dt. So we use the entropy generation, the flux we easily obtain Js x plus dx minus Js x means at the point x and the dx, the point, the entropy flux minus at x point entropy flux is the flux difference times area A. Here is the entropy generation ratio. Also, the ratio is equals AJQ times 1 over T x and dx minus 1 over Tx. Here is another equation. Entropy flux is not conservation. there is some change. So the entropy generation ratio, gamma, finally we can calculate is AJQ d1 over t over dx times dx. Because A dx just is the cubic meter, is the volume. So dV is dV. So gamma equals JQ d1 over x dx over dx times dV. Here is the entropy generation ratio. The total entropy generation ratio of the bar is delta Sg equals A from 0 to L integration JQ d1 over t over dx times dx. Finally, we obtain this equation because 1 to L integration is easy. Here is dt over t power second. Finally, we obtain this equation. Very easy to obtain. AJQ t1 minus t2 over t1 times t2. Because t1 always larger than t2, so delta Sg is always positive. We discussed the conduction problem. Give you a homework, calculate the entropy generation ratio of convection problem, like this picture. Okay, we have learned many knowledge about the exergy. We conclude about the exergy aspects. 1. Exergy is a measure of departure of the state of a system from that of environment. It is therefore an attribute of the system and the environment. The second, the volume of exergy cannot be negative if a system is at any state other than the dead state. The system will be able to change its condition spontaneously towards the dead state. In this process, we obtained also, or to say, the system can deliver some work, some exergy to the people, to the user. Thank you very much.